Well, good evening. It's 6 p.m. Eastern Standard Time, and I'm Charles Schultz, and this is the Randomizer for the 3rd of May, 2022. And tonight's subject is going to be petrophysics, literally the physics of rock. And so, what would be so fascinating about rock? There'd be a whole field of physics and study behind it. Well, the fact is, rock has many properties that we don't know about in our pedestrian existence. There are many things that we take for granted, and some of them are absolutely wrong. So let's have a look at petrophysics here shortly. First of all, I want to encourage you to go to schultzlaboratories.com or universeciencecenter.com. Put on your Oculus if you have a 3D headset, or your Vive or any of the other models, and walk around in our galleries and experience some of the exhibits we have and interact with some of our exhibits that we have that provide you with the ability to test things. We have places where you can put a satellite in orbit and see how circular you can go. We have digital logic gates you can watch in operation, and many other things coming. If you become a member of Schultz Laboratories, you support the growth and addition of more galleries, more interactive content and exhibits. If you also are an educator of some sort, have some skill that you wish to share with the world, or even just works of art, we can create a virtual gallery for you to put your works on display, and also a digital classroom where people from all around the world can listen to your lectures and learn from you directly. So, on the Randomizer, weekdays, 6 p.m. Eastern Standard Time. Join us with your questions, concerns, comments, whatever thoughts you have on the subject at hand, and we'll try to answer your questions for you. So let's get down to the material at hand, petrophysics. So what's so fascinating about rock? We think about rock as this durable, solid, inflexible material. But when you start looking at what really goes on in the world over time scales beyond our personal perception and experience, you'll find that it has very different properties from what you expect. Many people used to make taffy in times past, a simple candy. And part of the process was stretching and folding the taffy to give it its consistency. And one of the things that you will learn very quickly when working with candy, such as taffy, is if you pull it slowly, it will deform and change form without any issues. It will fold, it will wiggle, wrinkle, but if you move it rapidly, it snaps. Now, believe it or not, rock has the same properties. Over time, if you flex it slowly and gently, rock will deform just as taffy does. And so it's not unusual if you drive across the country in the United States, for instance, where we have many hillsides that have been cut through to make room for highways, bridges, passages. You will notice that there were layers of rock in place in many cases where the rock has literally turned into sinuous waves. And you're wondering, how in the world did a rock get folded like a sheet of paper? And the answer is, when the force is applied over extended periods of time, geological periods, the rock can literally flow. So our ability to see rock as a solid that fractures when you stress it has to be tempered by the perceptions of time. If we look at it over long periods of time, rock can literally, it can shift, fault, or fold in any way. Now, one of the properties of rock that allows it to do this is the content of fluid. So if you can imagine a stale piece of bread being flexed, it will crack. But if the bread were moist, then you may be able to fold it. The same is true for many minerals. Consider that we think of minerals as being impervious to liquids, watertight. Well, in many cases that seems to be true, but stop and think. When you see some minerals, such as limestone, it's pretty obvious that limestone is actually rather porous, and a lot of water can soak into it. I mean, you've seen sand. Wet sand will stick together and clump. You can build sand castles with it. Dry sand will literally flow through an hourglass and won't take a print or a form of any permanence at all. So what percentage of moisture has to be present to make the sand coherent? It doesn't have to be much. 0.5% by weight can be enough to make the sand stick together. And in researching it, you find the best way is to take a sample of damp sand, see if it takes a print, dry it out, weigh it, see what the difference is. Dry or desiccated sand gives you a dry weight. Could we do the same thing for rock? Absolutely. So limestone, as it turns out, is quite porous and will literally allow water to pass through it like a sponge. Not directly, but slowly over time. And this is why we see water dripping in cave formations, many of which are limestone. Well, what happens to rain when it falls onto the earth? What happens to the water that seeps into the beds of rivers or lakes? Much of it will enter the rock strata below and flow through it. This rock layering beneath these bodies of water can act as a filtration system, cleaning the rain and making it very pure. In many cases, the water we get out of a well is extremely pure, no biological signatures in it to think of if it's been underground for a long time, and it's been filtered through rock strata, and it usually contains some dissolved minerals that are actually quite essential for our nutrition, for our health. So well water, if it's from an uncontaminated well, can be very good for you and can carry minerals to you as well. And you know that water had to get underground somehow. It flowed through the rock strata. What about denser rocks, such as granite? Well, granite itself can actually soak up some water, and it's because granite typically is made of three minerals in combination. So think about making a soup and mixing different vegetables and materials together and then freezing the soup. So you have all these inclusions of different vegetables in it. Now, this is a little different. Molten rock that's been influenced by the presence of water can form granite if it contains, for instance, three specific minerals: quartz, mica, and feldspar, melted in their molten and dissolved state. They each have their own identities chemically, but in this molten state, they're mixed up almost like salt dissolved in water. So what happens when it begins to cool? Well, it depends on the rate of cooling. So if the rock cools slowly, the crystals of the minerals form in it, just like crystals growing in ice in the freezer, or just like crystals of salt or rock candy growing out of a solution. And as the crystals grow, the impurities from, let's say, the quartz get forced out, and the feldspar and the mica get pushed aside, and they grow their own structures. So granite is a composite of three minerals, and it doesn't always have to be those three, but typically it is. There are other similar materials like diorite that look very much like granite, but have different mineral combinations inside. Now, what's interesting is quartz is not so susceptible to water permeating it as, for instance, feldspar or mica would be. Well, as it happens, water can soak into those two components of the rock, and different things happen. Feldspar, when it gets wet, can undergo a transformation of its chemistry known as hydrolysis. Feldspar, straight from the volcano, is a dry, let's see, it's got a hardness of about 6 to 6.5 on the Mohs scale. And that hardness of rock, typically you'd think that's a pretty tough rock, it's not going to go anywhere. But water, when it reaches the surface of feldspar, changes it chemically and forms what's known as benthic clay. So feldspar decays in the presence of water by chemically turning into a type of clay. This is one of the ways that granite can erode. Mica is a layered mineral, and it can also permeate with moisture. So now you can see that there's one mineral that can literally be transformed by water in granite, and one that can literally pass water through it almost like a sponge. So granite itself has the capacity to, well, to imbibe quite a quantity of moisture, and it can even allow it to filter through it just as limestone does, but much more slowly. So different types of minerals can allow different fluids to pass through them. Now in petrophysics, typically we don't look so much as the folding capability of rocks. We don't look so much at the type of minerals themselves as to whether they have been transformed by heat or pressure and other forces. And we don't look so much of it as just types of minerals, but by their properties. So when we're surveying for oil underground, petrophysics becomes extremely important because different densities and types of rocks will reflect sound waves or the propagation of vibration in the ground in different ways. Some are more transparent, some are less transparent. And just like putting glass, plastic, water, oil in layers and watching how the light refracts through it can produce an interesting set of optical effects, sound waves or vibration traveling through the ground and the layers of rock do exactly the same thing. So we can use this to actually image what's happening underground. By setting off small charges on the surface and placing seismometers, seismic microphones around, we can record the patterns and timings of echoes and reconstruct a picture of the ground just like an X-ray or an MRI or a CAT scan, so we can see what's underground. What influences the rock can be different depending on the fluids carried by the rock. If there's oil in a substrate, it can soak into the minerals and produce a unique type of signature. If water is in the substrate, it produces a similar but different signature. So we can look underground and find salt domes by their density. We can find layers of shale or limestone or granite by their hardness and density. And we can also detect the presence of oil, water, or gas underground, natural gas, such as methane bubbles trapped underground, in the same manner. So most of petrophysics is interested in petrology, petroleum work. And think of the name petroleum. Petros actually means stone or rock. So when you talk about petroleum, you're talking about liquid from rock, and that is the oil in rock. There you go. Petrology and petrophysics deal with the physics of rock and the contained liquids in them. So now, why is this so important? Well, your water table is formed mostly by water seeping in at the near levels from the surface. Oceans, lakes, rivers, rainfall, that sort of thing. But understand, water didn't just come from the top of the ground. Much of it is formed by the chemistry inside rock in our planet. So if you have chemicals trapped underground at the time that a planet is formed, such as methane, ammonia, carbon dioxide, many of these materials are volatiles. When heated and compressed and placed in contact with those minerals, undergo transformations. What the most interesting characteristic of all of these volatiles is they contain hydrogen. And hydrogen is 2/3 of a water molecule. So when you have chemicals that are carrying hydrogen and they're heated underground, and ammonia is a perfect example, when ammonia is heated and pressurized, it becomes very chemically active. The hydrogen splits off the ammonia and reacts with the oxides in the minerals and forms water. The nitrogen works its way to the surface and makes up the nitrogen in our atmosphere. So, if you wonder why there's so much nitrogen in our atmosphere, it's because there was a huge budget of ammonia trapped in the bulk of our planet early in its history. What about methane? When methane is heated under these conditions, certain metals, such as iron being hot, for instance, is a catalyst for splitting ammonia and splitting methane. Methane loses some hydrogen, which forms water. It bonds to other split methane, and it becomes a higher order alkane. A hydrocarbon chain is growing in this process. And what do we call it when methane polymerizes underground and produces water in the process? Petroleum. Petroleum is not dead dinosaurs. It is literally the methane of the solar system trapped in the bulk of our planet during its formation, heated and cooked and fractioned into petroleum. So, when you're mining petroleum, you're actually getting some of the reduced lifeblood of the planet from its formation. And the hydrogen that is released in the process forms the water. The water dissolves certain minerals. Siderophile metals, such as copper, are part of that process. When we find native deposits of minerals in quartz veins on the surface of our planet, such as gold, platinum, silver, or copper, these are the four most common types of metals reduced and dissolved. Quartz, siderophile metals or precious metals, platinum groups, and water work together, dissolve and form veins. And when the veins reach a point where they're trapped in a crack and they cool, and the quartz crystals begin to grow, they exclude the impurities, the metals. What forms in the voids between the crystals? Copper, gold, platinum, and silver. And this is why we find native metals in stream beds near quartz deposits. The signatures underground are the presence of salt domes, trapped bubbles of oil, and salty water. These are the signatures of the chemistry that produced oil in the first place, deep in the crust of our planet. Using sonic methods and seismic waves, we've now discovered huge oceans of water deep inside the mantle of the planet. It is estimated there's between 5 and 50 times more water in the body of our planet than there is in all the oceans of the Earth combined. So the great questions that astrophysicists and cosmologists are wrestling about, where did the water come from? Oh, comets brought it to our planet, or asteroids brought it to our planet. Well, it turns out when they surveyed comets and asteroids, neither of them had enough water. And there's a cute signature that goes along with that, a fingerprint, if you will. Isotopes. Hydrogen that's exposed to space and water formed in space tends to have a lot more heavy hydrogen or deuterium in it. Hydrogen in the water from deep inside our planet has very little deuterium in it. There's a second. Oxygen in space is often enriched with oxygen 18. Oxygen in our planet is usually very poor in oxygen 18 and consists mostly of oxygen 16. So the water we find inside our planet has been there for geological ages, 4.5 billion years. And that water is ancient, and it's made of oxygen 16 and protium, basic hydrogen. Water from space often contains oxygen 18 and hydrogen 2, deuterium. So if the signature of the water from comets and asteroids doesn't match the signature of water coming from within our planet, then it's from two different sources. There's your proof that the water in our planet was formed inside and is forming our oceans and the water in our environment. So, petrology and petrophysics, the study of petroleum and minerals and their properties, leads us to some fascinating discoveries and methods of measuring properties inside the bulk of our planet. Asteroid fragments coming to Earth verify much of this because of the crystallization of molten iron in these small mini-planets. We find that they were formed under compression and slowly cooled to form large crystals. If you ever have a meteorite that contains iron and you slice it open, polish the surface, and etch it with an acid, a strange thing will happen. Crystal patterns will show up. They're called Wittgenstein lines, and they are the domains between the crystals formed in the slowly cooling molten iron that was in a protoplanet and smashed to bits and pieces of it fell to the Earth. We know that those same patterns can only exist if the cooling occurs in a very slow manner, which means it was inside a molten body. Well, petrophysics is a fascinating field, all about minerals, their structures, their reactions, and how they affect our environment. And I hope that you've learned something interesting from this talk. Now, if there are any questions, the floor is open. Meanwhile, I'm going to encourage you to go to universesciencecenter.com or schultzlaboratories.com, sign up, become a member. Help us get these words of knowledge out to everybody. Help us build more galleries, exhibit more things, more interactive content. Help us share knowledge with everybody. Well, I see no questions, so I'm going to read my quote for the day. And it is, "Who himself bore our sins in his own body on the tree, that we, having died to sins, might live for righteousness, by whose stripes you were healed." And that's 1 Peter 2:24. Take these words of faith, think, study, and learn. And I hope that you've learned something here today. Well, this is the Randomizer. I'm Charles Schultz, and I hope you had a great evening and make the world a better place. Thank you.